Hi guys, today in this video I'm going to show you the app developed by our team recently for radiation patterns. So using our application you can extract the radiation patterns and almost any other radiation parameters of the antenna from these popular full wave simulation softwares like Ansys HFSS and Dassault Systems CST Microwave Studio. So without wasting the time, I am going to show you the features and capabilities of the developed application in extracting the various results from these popular softwares. So I will start off with the HFSS software. I am going to consider the patch file as the reference case. So by clicking the solve frequencies, it will show you the adaptive solve frequency. If there exists nothing, it will show you a message in this window saying that no solve frequency exists for the currently selected design. So I will move on with the solution type of sweep type and fetch the solved frequencies. These are the solved number of frequencies for the sweep type. There you can choose any number of samples for the sweep type solution. So I'm going to plot the result for the 5.2 gigahertz since the adaptive frequency and the sweep frequency are matching over here. And the component that I'm going to plot is the gain component, and in the cut plane phi equal to 0 and phi equal to 90. You can control these values from these angles. And the plot mode, these are the various plot modes that you can get, and I will show you in detail every plot mode down the video. So I am going to plot the basic polar patterns using this application. So by clicking on Visualize Pattern, something will run in the backend using the Windows COM object, and the HFSS will give the data to MATLAB. So you can see the image being popped up over the screen. This is the image that you get by plotting using the application, and you can see the image being saved in the current directory from where the MATLAB application has been launched. I will show you the plot using the Windows Photos app. So this is how the image will looks like, and I will show you a number of images how they look like when they put together in a Microsoft document like docx or the window Microsoft presentation purposes. So moving on with this, I will show you the normalized patterns too. All you need to do is simply check this checkbox and click on the Visualize Pattern. So now you can see the normalized one. As you see on the screen, this is the normalized gain pattern. You can see the maximum has been fixed to a 0 level, and these are the patterns in phi equal 0 degrees and phi equal 90 degrees plane. And one more feature that I would like to show you is you can check on this export box so that you can get the simulated data in the form of CSV file. Like you can open using any notepad or Excel application. So here it is, the Excel file. You can see the file name too, file naming convention too. Here it is. AEDT means HFSS, and followed by the project name, and followed by frequency name, and followed by the cut planes and the type of the plot that you have selected in the application. So these are the three columns available in the CSV file that is exported right now after the plotting has been done. So don't save, and I'm gonna close this figure window. And one more feature that I would like to show you is the measured. You can compare the simulated data with the measured one too. When you check on this measured box, it will ask you to select the measured data file. It will perform certain validations before accepting the file that you have given to the application. And I'm gonna select this data. This is where my measured data has been stored. And if everything is fine with the formatting and all other things, you can see the file name that you have selected for the measured data, and click on Visualize Pattern. Just wait for a moment. You can see that in here you can see the simulated data has been labeled with SIM and measured data has been labeled with MEAS, measured, and the corresponding cut planes 5 equal 0, 5 equal 90 degrees. You can control these names by using the custom plot controls. I will show you how you can do it down the video. So for now, I am closing this image and unchecking this measure tick box, and I will show you the custom plot. So here you can see the 2D pole. These are the default inputs that you should be giving to the application for proper working and good looking plots. I can say they are good looking plots. And these are the color controls and marker specials, and this is the legend location control, and this is the label that you want to give to the plot. And so I will once again click on the Visualize Pattern, and you can see the labels has been now been changed to XZ and YZ plane. So you can see previously they were phi equal to 0 and phi equal 90 degrees, but now they are the customized that is being represented over here, XZ plane and YZ plane. You can give any random names over here separated by a semicolon, and you can see the vertical scale being labeled with gain in dB, which has been presented over here. And this is the polar part, and this you can control this Y range with the help of this control provided over this text box, and you can control this step size too. Here I have chosen 10 as the step size. You can choose something like 20 or 25 as per your convenience. And we'll now see the co and cross pole, the most interesting part of this application. Click on Visualize Pattern. Now it will show you the co and cross pole patterns at 5.2 GHz. As you see, the co pole leading the cross pole. So you can say the antenna has been performing much better at this particular frequency 5.2 GHz. As you know, the patch antenna has one solid frequency at which the co pole will be stronger compared to the cross pole, and this is the frequency where the patch antenna is working in a very fine manner. And now you can also change the constant plane too. I will go with theta equals 0 plane to see how it looks like, and I will change the step size to 40. So this is how the co and cross pole pattern and theta equals 0 plane looks like. You can vary the tick step to some other value. I have chosen the 40 as the tick step, so it has eliminated all in between values in the label format. We will now see the co and cross pole measured quantities along with the simulated also. So I will click on this measured property, and it will pop up to ask me about give me the measured file data. So I will select this co and cross pole data in the 50 plane, and as the file is formatted properly, you can see the name of the file being reflecting over here in the text box provided in the application. Now I will click on this Visualize Pattern button again to see how the results would be, and just taking a moment to load the results. Yeah, you can see the result plot on the screen clearly. As you see, the co and cross pole patterns are much similar, as simulated and measured data are very much alike in most of the region except for the nulls. And you can see the measured cross pole is better than the simulated cross pole quantity, so the antenna is performing very much better. And I will show you the same scenario with the 2D plot, with the rectangular plots. Now up until now we have seen this thing called polar patterns. Now we will move on to the rectangular plots. So I will show you the rectangular version. So I will click again the measured quantity and I will click data code 50, and now I will plot the same thing again, but in the rectangular plot mode. So you can see the difference between polar and rectangular plots, and I will show you the advantage of using the custom plot options also here. So you can get the maximum benefit of utilizing this application, and also you can save the time as well. So as you see on the screen, this was the rectangular plot I'm speaking of, and the same thing stretching the region from -180 to 180, and the co and cross pole patterns can be seen clearly with the indicator labels. Now I will show you the exact advantage of using the custom plot controls. So I will I will select the plot mode again, and as you see, these are the default inputs for the co and cross pole rectangular plots, and I will make a modification over here in the X range, and can now I will now change the position of the legend in the plot so you can maximize the plot window. So click again visualize pattern button. So this is how you can play with the controls provided in the compare plot controls, and you can provide you can obtain a maximum advantage, and you can also scale this X range to Y range. Here I have chosen the -50 to 10 with the step size of 10 as the limits for the Y range, and I will now change these values, so something like 70. So you can have the plots without any interruption with the legend, and this will be reduced to 0 because I am going to plot the normalized version of this plot. And strip size, okay, I will leave it like that, and click on visualize pattern again. So sorry, I didn't select the normalized version mode. I will select the normalized thing and click on the visualize pattern. So this is how a normalized version of this plot looks like, and now you can see the legend being freely placed over in the plot without interrupting the data presented in the graph. And many times you may want to choose a different label than what was interpreted in the application, so you can modify the names from this legend thing separated by a semicolon over here. And now we will see the 3D plots. So here are this 3D option, and I will now select the visualize pattern. Plotting 3D patterns for patch antenna may not be a visually appealing thing, but for the sake of showing the capabilities of this application, I am showing this 3D pattern. But you can extend this plotting capabilities to some array antennas where the 3D plots contain visually appealing beams, like radiating into free space in a particular beams, or you can use this to plot the radiation patterns of the reflector antennas. And one more thing, here I'm left with this gain and efficiency thing. So this was the most interesting part. So many of the times you may confuse with the radiation and total efficiencies, so you can choose in between these two quantities. So I'm going with the total efficiency as a first part, and leave it this combine box unchecked and measure the two. If you have some measured data, you can just click on this plot and then select one of your files over here. But now, as I'm not having the gain and efficiency data, I am going to skip this and checking. Okay, I will now click on the total efficiency, visualize pattern button again. It will take a little bit of time as there were a good number of frequency points defined in this field, so it will take a little bit of time to give you data. So here it is, the gain thing and the efficiency. This is the gain and this is the efficiency. As you see, the antenna being resonating at the 5.2 gigahertz, so you can obtain the maximum gain and maximum efficiencies. The gain that is being plotted over here is the realized gain in both CST and HFSS softwares. So I will now plot the combined things. So I will check this combine box and click on the visualize pattern again. So I will wait until the window again pops up indicating the data. So here it is, our plot, and I will show you the custom plot again using the advantage of custom plots. So I can get rid of this legend being overlapping with the plot data. So here I will go with the custom plot settings, and be careful with this X range over here because our simulation range extends from 4 to 6 gigahertz, but here it is minus 180 to 180. So you may get irritated with the plot that is obtained over that such a wide range, 4 to 6 and a semicolon. So I will leave it like that, so it will prompt me to enter in the profit format 4, 6 separator base comma and a step size of 0.25. 0.25 would be appearing, I think. And y range would be minus 9, okay, minus 10 to 5 with a step size of 2.5. And this sy range is corresponding to the efficiency thing because we checked the combined thing, so you are getting the both gain and efficiency things in a single plot with the combined with the respective y-axis on the left and right hand sides. And so okay, I will leave it like this. Okay, or else we'll go with 0.6 because the maximum efficiency achieved in the simulation is 55 to 58%. So I will I will move on with this 60% thing. And okay, the main thing is to use this legend location northwest. Where is this northwest thing? Yeah, here it is. Okay, click on visualize pattern. Now we will see where the legend is appearing in our plot again. Okay, 1 second. We are giving the wrong default inputs to the application. So here again, I'm clicking the visualize pattern. And yeah, you can see the green bar in the HFSS window. Yeah, here get this thing actually. Okay, this was quite disgusting. You can, as you see, you can have control this X range and Y range and the legend thing also. And one more thing to notice over here is the legend has been expanded in a horizontal manner rather than cascading in a vertical alignment. So can see this thing with the maximum efficiency close to 60% and the gain close to 5 dB. And we'll now move on to CST plot controls. Now I will show you how the CST will respond to this application when you query the required results, and we'll show you the most anticipating part at the end of this video, that is comparison of the results between the CST and HFSS in a single plot. So here I have opened this CST project already to avoid the delay in video. So it will promptly show us the solved frequencies. These are all the solved ones, and as usual I will show you a single and simple polar pattern initially, so you can see how the CST is responding to the application. So this is how the pattern has been extracted from CST, like in a couple of seconds, and you can actually export this data. As you see, as I explained earlier in this video, you can click on this export box if you want the simulation data to be exported out of this simulation software and you want to use it in any other external plotting thing. And okay, now we will see firstly we will see how the co and cross port pattern look like with the normalized enabled, the normalization. So this is how this looks like. Okay, I will now change the tick step size because this scale looks clumsy. We'll go with a scale of 40, the step size of 40. Now you have a better visualization of the scale thing. Also, you can control the scale limits through the custom plot controls, where I have shown you. Yeah, this is the Y range, and you can see the Y range being edited over here. Let us say if we want to plot between -100 and 0, with a step size of 25. We'll see how this plot going to respond to us. So these are the default inputs. I'm going to click the visualize pattern. Yeah, you can see this 0 to -100 thing with a step size of 25. This is how you have controlled the appearance of the plot using the custom plot controls provided in the window. You can actually edit this legend thing, and I'm going to 3D pattern thing again, just to show you the how it looks like for CST thing. It will take definitely couple of seconds only. Yeah, so we're done with the 3D pattern thing too. We'll now move on to the gain and efficiency. Here also, but I will now select the radiation efficiency thing and tick step, and this was the most controlling thing in the plot, so you have to choose carefully gain and efficiency. It will take a couple of seconds or less. Okay, it was taking more than a couple of seconds actually, like 7 to 10 seconds. Yeah, now you have the gain plot and efficiency plot. Because I didn't check the combined checkbox, you are getting the 2 plot windows. Now I'm going to check this combined thing and plotting this total efficiency. If you have something like broadband monitor, it will fetch the solved frequencies from the broadband monitor itself, or else if you have something like discrete number of frequency points, it will fetch the gain and efficiency things from those discrete frequency monitors. So here it is, the gain and efficiency. You can also choose in between them this radiation and total quantities, as I said earlier. And now we'll now move on to yeah, the comparison thing, like I said earlier, the starting of the video. So here you can see the entire controls in the CST being disappeared, and only you are left with these controls in the HFSS GUI only. So now you have to select in between these values. I mean, in between these options, you have to select one thing. So I'm going with the 2D polar pattern firstly to see how these variables looks like, and just click on this comparison. Before that, I will show you how this export data works and how you gonna have this data in the CSV file format. So yeah, the data is getting plotted. So this is the thing with the application that you may like the most. There, this here in this step we have compared the data obtained in HFSS and CST softwares, and by utilizing the custom plot controls again, you can modify or choose any color for these curves and numbers and custom legends too. So I will show you now this export thing. So here it is. This is the exported file. Here you can see on the screen the CSV file where the theta, gain, and all other things. The first two columns of the data corresponds to the HFSS, and the later two columns corresponds to CST1. As you see in the E column, you can see the term called CST, and in the C column I will now show you the HFSS name. I mean AEDD, indicating the HFSS file data. So similarly, you can export the co and cross pole things also from the application, utilizing the application properly. Comparison of co and cross pole, but the only limitation in this comparison option is no, you can't compare the measured data with the simulated data simultaneously. Like both the HFSS and CST simulated data can't be compared with this measured thing. So I will now gonna compare this co and cross pole in phi equal to 0 plane at 5 and 5.2. Sorry for that. Now in the next step I will change this thing to 5.2 frequency monitor in CST. Because of this you might see the discrepancies in the plotted values. I'm gonna select this 5.2 GHz monitor over here and change this thing. Tick step 40 and click on compare. This is the way that the pattern going to look like when you plot them, when you plot in any other external software like Origin or in Excel or in any other kind of software. I prefer this MATLAB software because it can code this, it can embed this entire thing into a code and will keep on forever as long as you're working with antennas or in this field. So it will helpful for others too. So you can see the red curve being behind this blue curve is the copole in HFSS, and the blue curve being the copole in CST. Cross pole in HFSS is indicated by the green curve, and the cross pole in CST is indicated by the black one. You can see the maximum similarity between these two solvers of the CST and HFSS softwares. So in this way you can also confirm the simulation results that you have done in the both CST and HFSS softwares. And before closing the video, I will show you the gain and efficiencies too. Total efficiencies I'm going to compare. As I said earlier in this video, I will show you how these plots would look like when you put these images generated by this application together in a document file for the publication or presentation purposes. just a couple of minutes. You will have a look at that thing too. So here is the gain and efficiencies in respect to solvers. You can see the maximum efficiency has been achieved at some other frequency due to the solver inherited solver differences, but the gains has been obtained at this much similar frequencies only. But there is a difference between these maximum values too again. That is due to the mesh convergence or the solver inherited solver differences. Like I haven't used this adaptive meshing thing in the CST due to save the time of simulation, whereas the HFSS has used this FEM based solver like volume meshing kind of thing. Okay, so you can also have this custom plot things. When I click on any of these options, it will show you the default options. These are the default options for the gain and efficiency when you are going with the custom compare plots. And now it's time to show you the document where it is. Yeah, here you can see the Word file. Can see it actually. These are the polar patterns and followed by 3D ones fetched from different solvers and different antennas. This one, the 3D pattern on the left hand side shows the a radiation pattern generated by a probe fed DRA, and whereas the right side 3D pattern is obtained from the patch antenna, and followed by these 2D rectangular plots that I have shown you earlier in the video. So these are the normalized gain things, normalized to 0 dB, and these rectangular plots are again followed by these radiation patterns obtained from your reflect array simulations. You can have a look at the reflect array simulations previously posted in our channel. If you like the content, please subscribe to our channel. And you can see the gain and efficiency plots too. These are the gain and efficiency plots obtained using the application. And finally, the thing 2D radiation patterns in the rectangular plot mode. So this is how the plots are going to look like when you put them in a document for your publication or presentation purposes. I hope this video got your attention and you like the content being presented in this video. And if you want to use this application, please feel free to contact us, and the respective contact links will be posted in the description too. Thanks for watching. Do subscribe to my channel.